Good morning.
Good morning, ma'am.
Very good morning, dear. Okay. So in yesterday's class, we were since from some time we have started with functional dependency module, and yesterday we were briefing out how all these functional dependencies can be done. So because this is very important not only for your only for clearing the BMS, but for your future also, because you are all will be as a software engineers. So when you will be working as a software engineers in some company, because everything data you have to keep it somewhere. So because you will be doing your projects. So then how the data you have to keep, how to fetch all those, how should be values in the database, and how to save the memory, and how to access fast accessing of those data values to your front end. All these are required not only for your DBMS. Only studying DBMS is not the thing, but for your uh, placement as well as for your companies. Even you consider very whether it is a small or very big project, you definitely require a database. So when we speak about database is nothing but your tables. So how should be the tables? That's what we are seeing in this uh, chapter, functional dependencies and normalization. So in yesterday's class, we were seeing about functional dependencies. Okay. So X, suppose if we take two columns, X is one column, Y is another column. What is X? X if I consider your USL, and Y if I consider your name. Okay. So if I consider like that, whether X is functionally dependent on Y, your USN number is functionally dependent on your name. Yes. Because if I know your USN number, suppose if I say 1BY 19 MCA 02, if I say like that, a respective student name, who is the 0202 will be, who is 02 USN number Abhinav. In the same way, if I call 1BY 10 MCA, if I just say 02, so Pavitra is also 02 USN number, and Abhinav is also 2. So, but here the problem again in this is there is 1BY, here there is TD. So that's what the difference is. So now I have in my table, I have to uniquely fetch the data. So that's what here we are checking out. X is functionally dependent on Y. So then definitely if I call if I exactly call 1B1 TD 19 MCA 10. So who will respond to me? Definitely Rashmi will respond to me, because her USN number is 1TD 19 MCA 10. So then if I just say 10, complete your USN in 10, definitely Rashmi will respond to me. So is it not functionally dependent? Is your USN not dependent on your names? Yes, definitely. So then, okay. So this is what is called X is functionally dependent on Y. Holds if whenever two tuples have the same value for X, then must have the same value for Y. Okay. What is that line says to us is, so now I told 1BY, you have a student table. Now let me say that we have created one student table for third semester, where all your USN, all your name, all your third semester subjects, so 31, 32, 33, 34, all the subjects marks, and even theory lab marks, and finally we have a total column is there. Let us assume like that. Then we start entering your all details. So 1BY 19 MCA 01, like that we start entering all your values. So now we have entered all 50 students details. Now in 51st place, again if I start entering 1TD 19 MCA 010, what I'll get there? Already Rashmi's USN is been entered in the table. Now again I am entering. Okay, if I enter, should it allow? Okay, if it is allowed also, let us assume that it is allowed. So it is been allowed that you can enter the, one second. Okay, so in case if it is allowed, let us assume that it is allowed. So in your case, we have entered. Rashmi is also there. Already one row is there, but again I have entered one more row for Rashmi. So then, if I say 1 TY, 1 TD, 19 MCA, 10, then who will respond to me? Rashmi will respond to me. But suppose if I say one more column, one more row is also there with same detail, same USN, 1B, 1 TD, 19 MCA, 10. Why? If I say your USNs are same, then again there also, Rashmi only has to respond. I cannot say that 1 TD, 19 MCA, 10, instead of Rashmi, I cannot write there Ravi. Yes, that becomes wrong. Then that's what here it says functional dependency. If I say your USN number 1TD 19 MCA 10, when I say it is 10 is for Rashmi, wherever you write her name and USN, it should belong only to Rashmi. Yes, that's what here. X means your USN, Y means your name. So if I repeat also, what is T1? For any two tuples T1 and T2, in any relation instance, R of R. If T1, what is T1? What is small T1? One row. One complete row detail of Rashmi. Yes, if that is the case, that is X. The USN here, what we have taken X. So if it is completely, in case, if I have one more row, let us take T2. And there also, Rashmi details are only entered. If it is, if her USN is there, if a USN is matching, then definitely her name should be same. In the name column, Rashmi only should be there. I cannot take some other student name. Here I have taken 10. USN for Rashmi is 10, 10 in two rows. Then definitely in Y column also, there should be Rashmi only. Yes, so that is what is called as a functional dependency. So when I say name is Rashmi, I cannot say Rashmi and Ravi. Can I say like that? Rashmi in one, if it is USN is 10 and I say Rashmi is 10, Rashmi is USN is 10, and in one more column I write 10 as Rashmi 10, and instead of there Rashmi, if I have written Ravi, is it right? No, it is definitely wrong. Then we cannot call it as a functional dependency. That's what is called as a functional dependency. How do we represent that? We represent here X functionally determines Y. In R specifies a constraint on all relation instance R of R, written as X is functionally dependent on Y, can be displayed graphically on a relation schema as in the figure. Functional dependencies are derived from a real-world constraints on the attributes. So examples of functional dependent constraints, social security number is functionally dependent on name. Project number determines project name and location, that is P number, P name and P location. Then employee, SSN and project. So we are just checking with the employee table whether social security number is functionally dependent on name. Yes, that's what just now I told USN and your name. Yes, this is definitely fine. Social security number, because it is unique, definitely it will be functionally dependent on name. So then project number determines project name and location. So project number, so project numbers will be unique for all the projects. Yes. So when it is unique, definitely we can say it is functionally dependent on P name and P location. So in the same way, employee SSN and project number. Yes, I am the employee in BMSIT college. I am working for some project. For which project I am working? I am working for a DBMS project. And what is the DBMS project name? 18 MCA 31. I have my identity, my employee number. Then that is what SSN. And project. How many hours I am working? For one semester, we have some 40 to 40 plus hours we have. So is this not functionally dependent? Yes, it is functionally. If I say Drakshraveni is handling DBMS, means what? How many hours I have to take? Is it not unique? Is there any person who is already having the same name, same number? Is there also who is taking DBMS? No, only one person is taking. That's what here it is also functionally dependent on hours. So then examples of functional dependency constraints and functional dependency is a property of the attribute in the schema R. The constraint must hold every relation instance R of R. If K is a key of R, then K functionally determines all attributes in R. Since we never have two distinct tuples with T1k equal to T2k. So that is what is called as a examples of functional example of functionally dependent constraints. And yesterday also we were saying about inference rule. What do we mean by inference rules? Inference rules for functional dependency. Given a set of functional dependencies F, we can infer additional functional dependencies that hold whenever the functional dependency in F holds. So what it says, given a set of functional dependency, I have just told functional dependencies are what? It may not only with one-to-one, that is your USN and name. No, along with that also, I can say DBMS marks. I will add your USN and your name. Along with that, I will add your DBMS marks also, lab and theory. Yes, that is what is called as a set of functional dependency. Given a set of functional dependency F, we can infer additional functional dependencies that hold whenever the FDs in F holds. Armstrong inference rules, IR1, that is reflexive. If Y subset of X, then X is functionally dependent on Y. So what is the work of first inference rule? Inference rule says to us reflexive. So what do we mean by reflexive? If Y is subset of X, that is IR1, that is reflexive. If Y subset of X, then X is functionally dependent on Y. So what is the first inference rule? What is reflexive rule says to us? If Y is subset of X, then X is functionally dependent on Y. That is reflexive. What is the second property says to us? What is the second inference rule says to us? Augmentation. That is, if X is functionally dependent on Y, then XZ functionally dependent on YZ. So that is what is called as a augmentation. So if X is functionally dependent on Y, then XZ is functionally dependent on YZ. That is what is called as a augmentation. So how do we represent the notation? We represent XZ stands for X union Z. That is what is called as a augmentation. So inference rules for functional dependency. So what it is? Reflexive. If Y is subset of X, then X is functionally dependent on Y. So the same way augmentation, if X is functionally dependent on Y, then what? Adding both the values for XZ as well as YZ. So let us take a small example. Augmentation, suppose now your USN is functionally dependent on name. Okay. So now if I add DBMS marks for USN, DBMS marks for your name, will it change anything? It is same. For same Rashmi, Rashmi's number USN is 1TD19 Mca 10. And what is it functionally dependent on her name? Yes. If I say USN 10, TD 10, then Rashmi will respond. Okay. So for TD 10, I am adding DBMS marks. TD column and DBMS marks column. So in the same way, name, Rashmi's name and her DBMS mark. Is there any change here? I'm just adding both the sides DBMS mark. For her USN also I'm adding DBMS marks. For her name also I'm adding DBMS marks. So that is what is called like an augmentation. Yes, I can do that. So when I can do, when X is functionally dependent on Y, then only I can add for your USN the marks USN DBMS marks for both the sides, that is left hand side as well as the right hand side. Left hand side, what we have taken? We have taken USN. And what did we take in the right hand side? We have taken name of a student, that is Rashmi. So now I can add DBMS marks for her USN. I can add DBMS marks for her name. So then that is what is called as a augmentation. Next one, transitivity. You would have seen in your mathematics. What do we mean by transitivity property? If X is functionally dependent on Y and Y is functionally dependent on Z, then I can say X is functionally dependent on Z. So that's what here you would have studied in your mathematics subject. If Y is X is functionally dependent on Y and Y is functionally dependent on Z, then I can directly say X is functionally dependent on Z. So something like Rashmi's USN is TD10 and it is functionally dependent on her DBMS mark. Yes, fine. Her DBMS marks is functionally dependent on her name. Can I remove DBMS and I can say TD10 Rashmi is functionally dependent on name? Yes, because I've just removed DBMS marks from both the thing. Then I can definitely say yes, TD10 means Rashmi. That's what here this transitivity rule says to us. So IR1 means what? Reflexive. IR2 is what? Augmentation. IR3 is what? Transitivity. Form a sound and complete set of inference rules. Not only these, we have some more, that is decomposition, union, and pseudo-transitivity. So what is decomposition? If X is functionally dependent on YZ. Decomposition means what? Breaking. So now I have functionally dependent on YZ. So let us assume that 1 TD10 is USN is Rashmi and is functionally dependent on name? Yes. Is it not functionally dependent on DBMS marks? Yes. I have split it. TD10 means name, TD10 means DBMS marks. Is it not the same? Yes. So that is what is called as a decomposition. Now I want to combine both. Now I have USN is functionally dependent on name. USN is functionally dependent on name. Then USN is functionally dependent on DBMS mark. Then can I not combine both USNs and just write as name and DBMS mark? Yes, I can write. That is what is called as a union. So in the same way, pseudo-transitivity, what do we mean by pseudo-transitivity? If X is functionally dependent on Y and YZ is functionally WY is functionally dependent on Z, then WX is functionally dependent on Z. So that is what is called as a pseudo-transitivity. The last three inference rules as well as any other inference rules can be deducted from IR1, IR2 and IR3. This says the completeness property. So next we move on to a closure. So what do we mean? Now Rashmi is close to whom? Whether she is close to Spurti or still very close to Pavitra or Maithili. To whom she is very close? So that's what we are finding out here. So closure of a set F of FDs. How do we represent that? If set is F, then we write F plus. Means it is a closure of all functional dependencies that can be inferred from F. What is inferred? We have just now seen inference rules, and using them we can say whether it is a closure or not. So closure of a set of attributes X with respect to F is the set X plus of all attributes that are functionally determined by X. So X plus can be calculated by repeatedly applying. We can apply all the inference rules, calculate them, whether can I apply in first rule reflexive, can I apply second rule inference rule, can I apply third rule, second was augmentation, can I apply augmentation, can I apply third rule, that is a transitivity, and check out whether a set X plus is closure to functional dependency of F or not. That's what we are trying to do. So equivalence of set of functional dependency. Two sets. So two sets of functional dependencies F and G are equivalent if every functional dependencies in F can be inferred from G and every FD functional dependencies in G can be inferred from F. Hence, F and G are equivalent if F plus equal to G plus. Then we say it is a functional dependency. Definition: F covers G if every functional dependencies in G can be inferred from F. So that is what does it mean? If G plus is a subset of F plus. F and G are equivalent if F covers G and G covers F. There are algorithm for checking whether two sets, so whether they are closure or not. So now minimal sets of functional dependency. Set of functional dependency is minimal if it satisfies the following condition. Every dependencies in F has a single attributes for right hand side. We cannot remove any dependencies from F and have a set of dependencies that is equivalent to F. We cannot replace any dependencies, that is X tends to A in F, with dependencies Y is functionally dependent on A, where Y proper subset of X, and still have a set of dependencies that is equivalent to F. Every set of functional dependency has an equivalent minimal set. There can be several equivalent minimal sets. There is no simple algorithm for computing a minimal set of functional dependencies that is equivalent to a set F of functional dependencies. To synthesize a set of relations, we assume that we start with the set of dependencies that is a minimal set. Next, we move on normal forms based on the primary keys. So first one is normalization on the relation, and what is a practical use? Why do we require a normal forms? Then definition of key and attributes participating in keys. First normal form, second normal form, and a third normal form. So normalization, the process of decomposing unsatisfactory bad relation by breaking up their attributes into smaller relation. So what is normalization? So now you would have created a student table, and we have entered 51 student details into the table. And now if I again copy one more time, it will be how many 100 times it will be there. Is it really required to copy same student details 2 times? No, then we call it as a bad relation. So if I remove that, whether I am losing any data, that's what I have to check here. That is what is called as a normalization. What is normal form? Conditions using key and functional dependencies of relation to certify whether a relation schema is in a particular normal form or not. That is what is called as a normal form. So in the normalization, so we see whether first normal form, whether it is second normal form or third normal form. But in your syllabus, we have only 1, 2, 3 and BCNF. We don't have 4NF and 5NF. So then normalization is carried out in practice so that the resulting design are of high quality and meet the desirable properties. The practical utility of these normal forms becomes questionable when the constraints on which they are based are hard to understand or to detect. So the database designer need not normalize to the highest possible normal form. So usually up to 3NF, or we can see this, whether we can go for third normal form or can we go beyond that, that is a fourth normal form. So then what is denormalization? The process of storing the join. Now I'm joining your student details and department details. Then that is what is called as a join. So denormalization, the process of storing the join of higher normal form relation as base relation, which is in a lower normal form. Definition of keys and attributes. participating in keys, a super key of a relation schema R equals to A1, A2, A3, like this. We may have n number. So what is the super key? Is a set of attributes S subset of R with the property that no two tuples T1 and T2 in any legal relation state R of R will have the same values. A key is a super key with the additional property that removes any of all the attributes from K, will cause K to be super key and super key anymore. Then definition of key and attributes participating in keys. If a relation schema has more than one key, each is called as a candidate key. One of the candidate key is arbitrarily designed to be a primary key, and the others are called secondary keys. The prime attributes must be a member of some candidate keys. Non-prime attribute is not a prime attribute. That is, it is not a member of any candidate key. That is what is called as a prime attribute and non-prime attribute. Then what is the first normal form, which we have already seen with some examples? Disallowing composite attributes. In the first normal form, suppose if the table is there and how to identify whether it is in the first normal form or not. In that table, you should not have a composite attribute. What do we mean by composite attribute? Now, if I take only name as one column, and if I start splitting that column into first name, middle name, and last name, no, then this should not be allowed in the table. So that is what is called as a composite attribute. In the same way, multi-valued attribute. Multi means what? Many. So now location. So that's what in your department we have a location. So maybe your project is in Bangalore, but the same project is being virtually working in 2 other places. Then we write in the same table 3 times. So that's what, even that should be avoided. In how to avoid that? Split up the table. So attributes whose values for an individual tuple are non-atomic. Consider a part of definition of the relation. So yesterday we were also saying that. So department, in department table, we have department name, department number, manager SSN, then a location. So which is a primary key here? D number is a primary key. If we start entering the values to this table, we can see that in department, research, administration, and headquarters are the department names. What are the numbers for the department? 541. What is a manager SSN? These are the manager SSN. And the location is these 3 locations present in 3 different places. Then Stanford and Houston. So this is what is research thing is being used. And you can see these are the 3 where it is been repeated. So you can see in this table, in the C table, the research is 3 times repeated, number is 3 times repeated, and manager's SSN is also 3 times repeated. So here, what is this table? This is a redundancy, means research is repeated 3 times. Suppose let us assume that if so many employees are working, if it is 10 department and it is located in 10 places, then what will we have to repeat that 10 times? It is waste of memory. So how to make this table into a first normal form? Break this table. So how to break the D name, department number, D name, and manager as one table, and D number and D location as one more table. Then we can reduce the redundancy in the department table. Okay, so same normalization, the same thing can be also done in this employee in project. Suppose if the employee in project table has been compiled, so then what? SSN name, project, number of hours, and working. So you can see here again it is also a repeated things. So there will be a repetition in this part. So to avoid this, break this table into 2. That is employee in project 1, employee and project 1 as one table, employee and project 2 as another table. So then that will be reduced. What does the second normal form says to us? The second normal form says to us, use the concept of functional dependency or primary key. That is prime attribute, full functional dependency. What do we mean by prime attribute? Attribute that is member of primary key. So now your USN, your name, I have made these 2 as a candidate key. Out of these two candidate keys, I will take your USN as a primary key. So then these two are called as a prime attribute. Now you have your subject 31, 32, 33. Then those are called as a non-prime attributes. And what they say, fully functionally dependent. When you have a prime attribute, rest of the values should be completely or fully dependent on prime attribute. That is what is called as a second normal form. A relation schema R is in second normal form if every non-prime attribute A in R is fully functionally dependent on the prime key. So R can be decomposed into 2NF relation via two process of normalization. So let us see how we can do. So this is what here. So in this case, employee and project, divide that into 3 tables. So then we can say SSN and project number is fully functionally dependent on hours. Then SSN is completely dependent on employee name. Then employee number is completely dependent on name and location. Then employee, same way, one more table, you can see employee and department. So this also can be splitted like this. That's what is called as a normalization, making a splitting up or decomposing the tables. One more table, that is lots. So here property ID, country name, lot 1, area, price, and tax rates. So instead of writing like this, and where all these functional dependencies are not completely or not fully dependent, then we divide it into lot 1, lot 2, and lot 1A. 1A and 1B. So like this we can divide them. Then we can say that these tables are in the first NF. So that's what here you can see in this diagram, lot present in first NF. So whenever we say whether this table is in second NF, if I want to say it should be in second NF, first it should satisfy that it should be present in the first normal form. When we say it is present in first normal form, then we can say it is also present in the second normal. When we move on to the third normal form, it should be present in first and the second normal form. Okay, what is the third normal form says to us? Transitive functional dependency. So in your table, you should also have a transitive functional dependency. So how do we say? So we know that FD stands for functional dependency. X is functionally dependent on Z. Then we can derive two functional dependencies. X is functionally dependent on Y and Y is functionally dependent on Z. So just now I told your USN X. If I say X is 1 TD, 19 MCA, 10 means what? It is Rashmi's USN. So I told 10 is USN. Z is what? Rashmi name. Y is what? DBMS marks. DBMS marks of Rashmi. USN 10, DBMS marks. DBMS marks, name is Rashmi. Can I not say USN is functionally dependent on your name? Yes, that's what here. Social security number is functionally dependent on manager SSN is a transitive functional dependency since SSN is functionally dependent on D number and D number is functionally dependent on manager SSN. Then SSN is functionally dependent on name is non-transitivity since there is no set of attributes X where SSN is functionally dependent on X and X is functionally dependent on E name. So that is what is called as a transitive functional dependency. So the third normal form, a relation schema R is in third normal form if it is in a second normal form and no non-prime attribute A is in R is transitively dependent on the primary key. R can be decomposed into 3NF relations via the process of 3NF normalization. Note, in X is functionally dependent on Y and Y is functionally dependent on Z with X as prime keys, we consider this a problem only if y is not a candidate key. When y is a candidate key, there is no problem with the transitive dependency. Example, consider employee table where SSN, employee number and salary. Here SSN is functionally dependent on employee number and it is also functionally dependent on salary, and employee number is a candidate key. So fourth general normal form definition says that for multiple keys. So the above definition considers a primary key only. The following are more general definition taken into account. Relations must be multiple candidate keys. So in a relation schema, R is in a second normal form if every non-prime attribute A is in R is fully functionally dependent on every key of R. So that is what is called as a second normal form. So then just definitions of the super key. Just now we have seen a super key of a relation R is a set of attributes S of R that contain a key of R. A relation schema R is in a third normal form, that is 3NF, if whenever functional dependencies X is fully functionally dependent on A holds in R, then either X is a super key of R or A is a prime attribute of R. Boy's code normal form disallows condition B. What is BCNF? BCNF, a relation schema R, is in a Boy's code normal form, that is BCNF, if whenever an functional dependency X is functionally dependent on A holds in R, then X is a super key of R. So when I say it is in Boy's code normal form, each normal form is strictly strong than the previous one. Every 2NF relation is in a first normal form. Every 3NF relation is in a second normal form. Every BCNF relation is in a third normal form. There exist relations that are in a third normal form but not in a BCNF. The goal is to achieve each relation in a BCNF or a 3NF. So we can see in this example Boy's code normal form. So Boy's code normal form, this is A with the dependencies, functional dependency 2 is being lost in the decomposition. So in the relation in the part B, you can see it is B because it is decomposed. So lots 1AX and lot 1AY is this table is being decomposed into 2. So now if we take small example, A is functionally dependent, A and B, so both it is a super key, means what, USN and your name is completely dependent on your marks. Then we say this is a relation. R is not, it is there in 3NF but not in a Boy's code normal form, because if I say your DBMS marks is not functionally dependent on your USN and name, then I cannot say it is in a BCNF. So let us take a relation teach that is in 3NF but not in BCNF. Now teacher, that is in a table teacher we have a column called as a student, course and instructor. So student names Narayana, Smith. So these are the student names. In the same way, course, Narayana has taken DBMS, Smith has taken DBMS, Smith has taken operating system, Smith has taken theory. Like this, all the courses. And who is teaching this? So the instructor name, Mark, Navate, like this we have. So whereas in this case also, in this table also, you can say a relation teach, that is a teach is a table name that is present in a 3NF, but this table is not in a Boy's code normal form. So to achieve this Boy's code normal form, so what we have to do, you can see here, still the Smith is repeated, course is also repeated, because main goal of normalization is try to avoid redundant values. So two functional dependencies exist in the relation teach. So that is student course is functionally dependent on instructor and instructor is dependent on course. Then student and course is a candidate key for this relation, and that the dependencies shown in the pattern in the figure 10-12. So this says that it is present in a 3NF but not in a Boyce code normal form. A relation knot in BCNF should be decomposed so as to meet this property, while possible for foregoing the preservation of all functional dependencies in the composite relation. So how do we achieve the BCNF by the decomposition? Three possible decomposition for the relation teach, that is student instructor, student course, course instructor and course student, instructor and course and instructor and student. These are the three possible ways where we can decompose the teach table. So all three decomposition will lose functional dependency 1, because what was a functional dependency says two composite or super keys are functionally dependent on that. So we have to settle for sacrificing the functional dependency preservation. But we cannot sacrifice the non-additive property after decomposition. Out of the above three, only the third decomposition will not generate surplus tuples after join. So a test to determine whether a binary decomposition into two relation is non-additive, that is lossless in the discussion. So under this we can say LJ1 verify the third decomposition above meets the property. So how should I decompose? I can decompose in the three ways, but which one is better? The better one is third one. So by this I complete your fourth module. By this we end with your fourth unit. So in the next class we'll try to have a fifth module, the last module in your syllabus. State is 11. Answer your attendance. Asta. Why, my dear, yesterday you were absent? Abhinav?
No, I'm not well.
Okay. Abhinav? Aishwarya?
Present, ma'am.
Amrish?
Yes, ma'am.
Anu?
Present, ma'am.
Arbaz? Arjun?
Present, ma'am.
Ashok?
Present, ma'am.
Benita?
Present, ma'am.
Bhargavi?
Yes, ma'am.
Bhavishya?
Present, ma'am.
Chaitra?
Present, ma'am.
Debmalai? Diksha? MS? Deepika LG?
Present, ma'am.
Deepika MB?
Present, ma'am.
Murli Krishna?
Present, ma'am.
Gangubai?
Present, ma'am.
Gudia? Harshit?
Present, ma'am.
Junjar?
Present, ma'am.
Kavya?
Present, ma'am.
Kishore? Lata?
Yes, ma'am.
Manisha?
Present, ma'am.
Manjunath?
Yes, ma'am.
Nayana? Nilanjan? Nishant?
Yes, ma'am. Present, ma'am.
Pavitra?
Present, ma'am.
Maithili?
Present, ma'am.
Priyanka?
Present, ma'am.
Pavan?
Present, ma'am.
Akash?
Present, ma'am.
Rajeshwari,
Present, ma'am.
Rakesh,
Present, ma'am.
Ramya,
Present, ma'am.
Rashmi,
Present, ma'am.
Ravi,
Yes, ma'am.
Rizwan,
Present, ma'am.
Vishal,
Present, ma'am.
Savita.
Yes, ma'am.
Yesterday you didn't answer, Savita. Shruti,
Present, ma'am.
Sneha,
Yes, ma'am.
Spurti,
Present, ma'am.
Srinidhi,
Present, ma'am.
Srinivas,
Present, ma'am.
Sunil,
Present, ma'am.
Vaishnavi,
Present, ma'am.
Vinny,
Present, ma'am.
Ma'am, Diksha, present, ma'am.
yeah, Diksha, Diksha MS, Yamat,
Yes.
yeah,
Ayana, present, ma'am.
Nayana. Nayana Mat. Okay. So people who have joined late can complete the quiz. I'm pasting the quiz in the chat window and I'll wait for some time for you people to complete. How many of you are absent today? Abhinav, Arbaz, 2, Tebmalai, 3, Gudia, 4, Kishore, 5, okay. Yes,
Ma'am?
Spurti.
Ma'am, what about college? Any news about
We were
that?
hearing since from yesterday in the news. I don't know about the official thing, but we were saying that if from December they will start. Don't know what they'll do. But for you people, they were saying it will start from 17th. But how it is, how far it is true, we don't know. We don't have any idea about that.
Okay, ma'am.
So we'll stop here. Continue.